v7sansitheater@gmail.com. You can contact us v7sansitheater@gmail.com. You like our videos? Today I want to teach you about membrane potential, and to start right away, don't forget that this is the V7 Sansi Theater. You subscribe to the channel. You like our videos, you comment. I will see the comments and I reply. Share our videos to other students and people who else enjoy. Don't forget to click the bell for more videos we upload daily. So as we go through the introduction to membrane potential, there exists a potential difference across membrane of all living cells within the inside, negative and relation to the outside. So this potential difference exists where the cell membrane on its inside we have negativity relative to the outside, which is positive. And this potential difference is named membrane potential because the cations and anions arrange themselves along the outer and inner surfaces of the membrane. You see there's an arrangement of cations and anions along the surfaces of the cell membrane. And the magnitude of membrane potential will vary from cell to cell, and also in a particular cell it can vary based on the function status of that cell. For example, a neuron, call it a nerve cell, has a membrane potential of about negative 70 millivolts when the inside is negative or at rest. But when it gets excited, the membrane potential will rise to about positive 30 millivolts, where the inside becomes positive relative to the outside. The resting potential indicates no electrical change, but the cell is still metabolically active. And the membrane potential measured during excited state of the cell is called action potential. When it is at rest, we call it resting potential. When it is excited, the cell is in an excited state, we call it action potential. And yeah, the point here is that the resting potential indicates no electrical change, but it does not indicate that the cell is metabolically inactive. All right. So how is the membrane potential generated within cells? It is basically due to an equal distribution of ions across the cell membrane, which in turn results due to combined effect of the various forces acting on the ions. The factors involved in genesis of membrane potential are basically five. The first two, we have selective permeability of the membrane. We have the Gibbs-Donnan membrane equilibrium. We have Nernst equation. We have constant field Goldman equation. We also have sodium-potassium H-phase pump. So today I want to talk about selective permeability. I'll also talk about Gibbs-Donnan membrane a little bit, and I will also talk about the purpose of the sodium-potassium H-phase pump. The Nernst equation and constant field Goldman equation, these two I'll talk about in another video because they have some calculations which I want to demonstrate. I'll be on board there and I'll demonstrate them to you, the calculations involved in the Nernst equation and the constant field Goldman equation, and to talk more about Gibbs-Donnan membrane equilibrium. So let's continue. What is the role of the sodium-potassium H-phase pump? This pump lies in building of the concentration gradient. To generate a concentration gradient across the cell membrane, the sodium-potassium H-phase pump is required. And what is its role? It will be pumping the sodium ions that diffuse into the cell out. And it will also be pumping in the potassium that diffused out of the cell. Right from the cell cytology, we saw that we have a lot of potassium inside the cell relative to the outside. We have a lot of sodium outside the cell relative to the inside. So At rest, it is inevitable to have sodium diffusing into the cell. So it is when it comes to potassium to diffuse out of the cell. But this pump regulates that. So this pump makes sure that whatever sodium goes into the cell is pumped back out of the cell. And the potassium which diffuses out of the cell is brought back into the cell to maintain stability of the membrane and the cell. So further, although the sodium potassium pump is potentially electrogenic because it is pumping 3 sodium out and 2 potassium inside, at no stage the pump is able to build up a significant membrane potential. The pump itself can't build up a significant membrane potential, though it is electrogenic, okay? So this is because as soon as the pump creates a negative potential inside the cell, the chloride ions rush out of the cell and restore electron neutrality. Thus, in other words, the pump pumps out 3 sodium ions and 1 chloride ion for every 2 potassium it pumps into the cell. I hope my point is clear. We will say it is electrogenic, the sodium potassium phase pump, alright? It is electrogenic because it is generating a difference in it is creating a certain electrical gradient. We have 3 sodium ions getting out, we have 2 potassium being replaced. So it means there is a difference of a charge here. So we would expect electrogenic effect, but this does not occur. Yes, there is no significant membrane potential just because as the sodium potassium H-phase pump is actively pumping out 3 sodium out, okay, a chloride ion will rush out of the cell and restore the neutrality. Therefore, it pumps out 3 sodium ions and 1 chloride ions for every 2 potassium ions it pumps in. Alright, so chloride was the major anion causing that occurrence in the previous page. So instruments used for recording the membrane potential are usually here. We have the microelectrodes. These are necessary to have them. We shall see the diagrams in the next video. We have electronic amplifiers. They are also important in amplifying the signals we have. We also have the cathode ray oscilloscope. This one is very important in measuring and recording the membrane potential. So let's begin by the selective permeability of the cell membrane. The cell membrane is permeable to some ions freely. To others it is impermeable, and some others it is permeable by variability. What am I meaning? Semi-permeability means that some ion selective permeability will be meaning that the cell membrane is permeable to some ions freely. To others it is impermeable, to others it is permeable at some extent. And the cell membrane is freely permeable to potassium and chloride, and moderately permeable to sodium. You get that point? Highly permeable to potassium and to chloride, and moderately permeable to the sodium ions. The cell membrane is practically impermeable to intracellular proteins and organic phosphate. Why? Because these are negatively charged. So it is impermeable to intracellular proteins and to organic phosphate. Okay, so Gibbs-Donnan membrane equilibrium. This I didn't expound more about it, but I want you to have some idea. For we shall talk more about it on the board when I'm calculating some questions we will see. And there are other video, not this one. So when two ionized solutions are separated by a semi-permeable membrane at equilibrium, its solution shall be electrically neutral. i.e. the total charges of cations will be equal to total charges on anions. Okay, so if you just separate two solutions which can ionize by a membrane, at equilibrium, each solution shall be electrically neutral. You get that point? Each shall be electrically neutral, and total charges on cations will be equal to total charges on anions. All right, and the product of the diffusible ions on one side of the membrane will be equal to the product of diffusible ions on the other side of the membrane. We're talking about products. Product of diffusible ions on one side of the membrane will also be equal to the product of diffusible ions on the other side of the membrane. So don't forget to subscribe to our videos. You like them, share. That was all I would talk about membrane potential. The Nernst equation and gives Donan equilibrium, membrane equilibrium. We shall talk about them in the next video. Not the next, but another video is coming soon. All right. Thank you for following. Thank you for